About thermodynamic stability, the various aspects that we have covered, nature of metal ion, nature of ligand, and about the nature of chelation or the ring size effect or ring formation effect. Last time I told you few points, means about the ring structure, means about the chelate, by which theory or by which concept we can say that chelation can give a stable complex or chelates are stable. For the 2 points, one about the bonding, because chelates are with the 2 or more number of bonds and it's very difficult to rupture all the bonds simultaneously or exactly. Student, just a minute. Sorry for disturbance. हाँ सूरज, हाँ काय केलं? हाँ तर लगेच पाहिजे का? लेक्चर झालं देऊ का? 12:30, सव्वा बारा 12:30. ओके, लगेच झालं की लगेच ते काम करू, तुला पाठवतो नवीन डिसाईड करू मुंबई. Yeah, I was talking about the chelation, and the chelation can be explained by simple concept, that's a bonding. Number of bonds are more and therefore the complexes are more stable. And second concept, that's a thermodynamic consideration. What was that thermodynamic consideration? What was that formula? Delta. Yes, delta G is equal to, help me to complete that mathematical expression. Delta G is equal to
delta H minus T delta S.
Right. T delta S, and we were interested more on what the change in the entropy. And with the help of reactions, I told you how is there change in the or increase in the entropy causing this term more positive, resulting delta G more negative, and the favorable state will be. Therefore, we say chelation gives the more stable complexes or chelates are more stable. Then about the chelates, which kind of chelates are most stable in detail further. Chelates are stable, that we understood, but among chelates, how can we decide the stability? For that, 2 points were there. The first point, number of rings, and about which I had a discussion. And second point, number of members in the ring. Higher the number of rings, higher the stability. And about members of the ring, 5-membered or 6-membered rings, expected was thoroughly, properly that ligand should arrange. So if there is no conjugation, means if there is no possibility of delocalization of electrons, then we can say 5-membered complexes are most stable, 5-membered ring complexes are most stable. And if there is a possibility of chelation or a possibility of resonance or delocalization or conjugation, then 6-membered rings are more stable. To make this concept clear, I give you one example. I repeat, about this number of rings I had a discussion last time. Today I am discussing number of members present in the ring. How can they affect the stability of the complex? For that, let us consider the example. Oxalato. You might have heard oxalato ligand or oxalate. Yes, will anybody answer what's the formula for oxalate? Yes, at least complete this portion.
Sir, whiteboard share nahi.
Whiteboard not shared. That I asked previously. Now anything which I'll bring up on my screen, you could able to see. Yes, could able to see that?
Yes, sir.
Yes, sir.
What's the formula? C2O4?
2 minus.
Right, brilliant answer.
2 minus.
Yes, oxalate ion, oxalato ion. It is a ligand. Here, whoever 2 oxygens are there, they govern the negative charge. Those oxide ion can be a ligand. So let me consider in general. Metal is at center and the oxalate is going to form the bond with that oxygen bearing negative charge. And one oxalate is with the 2 oxygens carrying negative charge. It is a case of one oxalate. Similarly, other oxalate, oxygen, which carries negative charge, for which that -2 charge is there. So here -2 charge, sorry, -1 and here -1, total -2 charge. Out of 4 oxygens, and this oxygen is linked to what? Carbon, which is linked to oxygen, which has no charge, linked to carbon to other oxygen, and these 2 carbons are joined each other or linked to each other. It is our oxalate representation. Similarly, this oxygen I am considering bearing negative charge. This oxygen also is carrying negative charge. This oxygen is linked to carbon. It also is linked to carbon. And one further 2 oxygens I need to consider, each on 1 carbon. So here double bond, double bond because it has no charge, therefore, and between carbon carbon there is a bond. So this is the oxalato complex. It's a bisoxalato complex or dioxalato complex, ring structure complex. It is a chelate. We have to find number of members in the ring. First member is metal, second member is oxygen carrying negative charge, third member is one of the carbon, fourth member is other carbon, fifth member is oxygen bearing negative charge attached to second carbon. So how many members are here in this ring? How many are there? 5 members are there, and this 5 membered complex is more stable, means bond angle if you consider or compare, no, then that's a 5 membered gives the somewhat good kind of comfort for the bond formation. Here don't think or understand that here 90-degree bond angle is there. So it is found 5 membered rings if there is a no conjugation, because here double bonds are not there inside the ring. So the delocalization of the electron, free electrons are not there. So delocalization of electron that we cannot find. If it is not there, then 5 membered rings are stable. It is the first statement of today's lecture. My main point is how many members should be there in the ring so that more stability will be there. An answer for that, if there is a no conjugation, if there is a no delocalization, if there is a no possibility of the spread of the electron within the ring, I am saying, then 5 membered rings are more stable. Is the conclusion of this discussion clear? Yes or no?
No.
No. Okay. See, oxalato is a point of discussion here. Ethylenediamine also we can consider, but miss where ligand should be with no double bond. Double bond within ring, I am saying. Here double bond is there between carbon and oxygen. Double bond is there between carbon and oxygen. But my focus is on the ring form here. Within this ring, there is no double bond. If such situations are there, then 5 membered rings are more stable. More additional explanation that I give it to you. Suppose if you consider triangle, then what is the bond angle here? Bond angle, equilateral triangle, 60 degree. If I consider say square, what is the bond angle? Yes?
90.
Right, 90 degree. If I consider pentagon, equilateral, all sides are equal. What's the bond angle? That you can consider any other bond angle. This angle or any other bond. Yes, this bond angle consider, this bond angle consider. What's the bond angle? Are you understanding what I'm saying? So in pentagon, what's the bond angle? See how to find simple way. Here angle is 60. Here angle is 90. How are you finding that angles or those angles? Are you following or not? Just let me know. Shall I give more explanation?
Yes, sir.
See.
Yes.
Let me consider one equilateral triangle. All sides are equal. Question was, what is this bond angle? You have answered that bond angle is 60 degree. Let you know how that 60 degree came. Two different ways are there, but uniform way I am saying, which we can apply for others also. Anybody want to enter? No. So how to find that? Just extend this line. You will find this external angle. And this external angle is equal to, what's the formula? 360 degree divided by number of sides. For triangle, how many sides are there? For triangle, how many sides are there?
3.
360 divided by 3. So it's a 120 degree. It is an external angle. This angle is 120 degree. But this is complete line. No, it's a 180 degree. So angle represented here, this angle is equal to 180. 180 means straight line, linear. Minus 120 is equal to 60. Therefore, this 60 came here. Could you able to understand this what I am saying?
Yes, sir.
Yes, sir.
Let us apply it again for other geometry. If I consider square, all sides are equal. As previous, I want to find external bond angle. This bond angle I want. What is the formula for that? 360 degree divided by number of sides. First side, second side, third side, fourth side. 4. Answer is 90 degree. So it means this angle is 90 degree. If it is 90 degree, then what is this angle? This angle is equal to 180 degree minus 90 degree is equal to 90 degree. Therefore, we said bond angle is 90 degree if 4 sides are there. Is it clear?
Yes, sir.
Yes, sir.
Now my question is, if you consider pentagon, what is this bond angle? Inner bond angle. Use the learning that I informed to you. Yes. What is this angle?
408.
408.
108.
108. Is it
72.
70? Yes, 10 is the right final answer there.
72.
72 degree is the external angle. The internal angle in which we are interested. This angle is equal to 180 degree minus 72 degree is equal to 108. Right answer. 108 degree. So I represent that answer now. When I considered 5 members in the ring, then bond angle. Why I want to find the bond angle? Because strain I want to find. 5 member, the bond angle is 108 degree. But if we consider 6 membered rings, it's a hexagon. What is this external bond angle?
60.
Right, 60 degree. Then what will be the internal bond angle?
120.
Right,
120.
20 degree. When we consider conjugation, means alternate double bonds, as like they remain in the benzene, then type of hybridization that atom here carbon especially undergoes is sp2, and because of that sp2 hybridization, where what is the bond angle in sp2 hybridization? Sp2 means bond angle will be, it's like a fan, bond angle between two plates of fan. Is my question clear?
120.
Right,
120.
120 degree. Yes, and it is matching. Means if 6 members are there, then 120 degree bond angle is convenient. Means 120 bond angle will be there if there is sp2 hybridization and there is a delocalization. Wherever sp2 planarity is necessary, no, for delocalization. To spread something plane is what necessary. Means when you apply the butter to the bread, then at that time a plane remains, no, so by means of knife you can apply that, by means of spoon you can apply that smooth region, plain region. Delocalization, spreading is possible. So for delocalization, planarity is necessary, and that is in sp2 hybridization. But if there remains sp3 hybridization, in case if you consider sp3 hybridization which is not planar, tetrahedral arrangement, what's the bond angle for sp3? 1 0. In tetrahedral arrangement, what's the bond angle? For example, methane, what is this bond angle? Yes, could able to answer the question. For sp2, as I said, 120 degree. So like tetrahedral bond angle, sp3 hybridization bond angle. Oh,
109.
right, 109 degree 28 minutes, something which is near to, means here it should be, it's a 109, and this 109 degree or 20 minutes is near to 108. So in such a cases, alignment is somewhat more comfortable. But if suppose if they compel to remain 6 member formula likewise here, then strain will be there. So wherever there is a less strain, that will be followed. But if it has to remain in the 4 member, then bond angle will be 90 degree. 90 degrees far away than 109 degrees. So more suitable is 5 member. Therefore, my statement was, in general, if there is a no sp2 hybridization, or if there is a no conjugation, or if there is a no delocalization of electrons, in such a cases, generally it is 5 membered rings are more stable. Is this conclusion clear?
Yes, sir.
If you consider as an example ethylenediamine, so nitrogen is one donor from the amine, other nitrogen I represent here. These are the donors. NH2 is a fine. It's because n nitrogens are there, but nitrogen is trivalent, so it has to form bond with carbon. Trivalent, it has to form bond with carbon, and carbon are related. It's like addition on ethylene. So to balance the valency, here two hydrogens, it is our ethylene diamine ligand. It will donate lone pair, here it will donate lone pair through its what, the orbitals. Which orbitals? Whatever the nitrogen undergoes one hybridization, you will answer me. Out of that, one hybrid orbital remains with lone pair and donated. This nitrogen also is with hybridization. Out of the hybrid orbitals possible, one orbital donates the lone pair. To whom? To central metal ion. Is one of the side. Only one ring I am representing. This ring is 5-membered ring. First member, second member, third member, fourth and fifth. Now let us find hybridization of each member. Will you answer? What's the hybridization of this carbon? Tetravalent, no double bond. Hybridization, at least
sp3
right. Hybridization of this carbon,
sp3
hybridization of nitrogen, NH3 means sp3. Here NH2 is there, but like NH3, other bond is there. In NH3, all three hydrogens are there. But here, two hydrogens, and in spite of one of the hydrogen, linkage to carbon. Hybridization is
sp3.
right, sp3 only. Means from that writing, if you are guessing, good. But I want that you should understand. And here also hybridization is sp3. Or if concept is not clear, I'll discuss this also later on. But time being, I want to inform each item is with sp3 hybridization. So planarity for spreading possibility is not there. So tetrahedral, and for tetrahedral arrangement, just I told you what is the bond angle. That bond angle is, or you only answered 109 degree 28 minutes. It is expected alignment. In that way wings are there. In that way arms of that nitrogen carbon are there. They are linked. But suppose if we arrange them in a square planar, suppose, then there will be strain because square planar will demand 90 degree angle. If we arrange them in pentagon, then it is somewhat convenient because demand is 108 degree. But if we arrange them in hexagon, planar arrangement, then demand will be 120 degree. What do you think? Which is the proper business for ethylenediamine? Pentagon or hexagon or square planar? Square planar arrangement not, because 5 members are there, no? Yeah. Which is from bond angle point of view 108 degree. And this bond angle is possible because of 5 members. Therefore, statement was 5-membered rings are more stable if there is a no delocalization, if there is a no conjugation, if there is a no resonance. Friends, is it clear?
yes sir
Yes, sir. Yes.
Yes. Now let us consider one more example where 6 members are there and delocalization or conjugation. In benzene, you know, in a similar way, how can we describe? For that, I am considering acetyl acetone as a ligand. So here CH3, I represent carbons also there. Means it will be easy for you. CH3 I represent, yes. And here it is linked to carbon. After us, we will balance the hydrogens. Carbon, it is linked to CH3. And here one will be the double bonded, one is what? Single bonded. If it is single bonded, then how will valency be balanced? That you have to answer. Means acetyl acetone, ACAC, it carries -1 charge, and that -1 charge is on one of the oxygen. Similarly, I have to represent other acetyl acetone. I represent it by different color. Oxygen, here other oxygen, I represent that. For the sake of brevity, I represent above oxygen as minus charge. So it will be with single bond. Below oxygen with no charge. So it will be with double bond. Of course, they are linking to carbon. They are linking to carbon via one more carbon, and here this carbon is linked to methyl group. This carbon is linked to methyl group. Okay, everything is not completed. Here if I see valency of carbon is fulfilled. Here if I see it is not. So how many hydrogens shall I consider here? How many hydrogens?
one
How? One. Total tetravalency should be there, no?
2.
Yeah, 4, 2. Okay. If it is there too. Suppose example. But problem is to oxygen. So problem is to this carbon because it is only 3. So what I have to do here? I have to arrange one more in that way. But in true sense, all the structure, how is the structure that I represent? Just here additional information I need to provide, then you will understand. Here there is a double bond. So if double bond, then of course it should be 1. So tetravalency for carbon fulfilled, here also fulfilled. Similarly, wherever that oxygen carries a negative charge, towards that side there will be double bond. So here I have to represent double bond. Here oxygen divalent fulfilled, tetravalent fulfilled, tetravalency not fulfilled. I have to consider one of the hydrogen. Now it is fulfilled. Here it is what? Fulfilled. So this is acetyl acetone NATO, ACAC minus ligand. And if I consider metal at the center and your bond formation is there, this oxygen which has a double bond in this way, just way of presentation I am saying. Okay, two different kinds of interaction. One interaction with O minus, other interaction with only O. For that represents different, but all are coordinate bonds. Now in this structure, you can easily read or understand there is possibility of delocalization of electron, as like in benzene there remains a delocalization, one electron, double bond, then alternate double bonds, alternate remains. So here there is a double bond, here there is a not, but double bond. So alternate double bond is there. Here I'm talking about ligand. Here alternate double bond, and here which are the bonds are there, the two electrons, so that we can understand in different ways. And the spreading of electron, which are the pi electrons are there, it is what possible in this structure. Here spreading of electron is what possible in this structure. Why? Because this carbon undergoes sp2 hybridization. This carbon undergoes sp2 hybridization. So I'm not discussing in detail because you know that, therefore if you do not understand then I'll explain that. But I want to move next now. sp2 hybridization. So sp2 all are planar. Planarity is there. So spreading may what possible. Planarity is there. Spreading may possible. Or because of planarity, the bond angle expected here during bonding, sp2 expectation is 120 degree, and whatever the 6 bonded planar arrangement if we consider, then also their angle remains 120 degree, and then which is matching. Therefore for such a 6 membered, first member, second member, third, fourth, fifth and sixth, so 6 membered rings, number of 6 membered rings, delocalization may what possible, or where ligand itself remain with such conjugation or ligand remains with sp2 hybridization, they prefer 6 membered rings rather than 5 membered. So 5 membered or 6 membered are in general stable rings. Students, are you following what I'm saying?
Yes, sir.
If no, then say no. Let me give the other angle of explanation. If anywhere problem is there, then also bring it to my notice. Waiting for replies from others.
Yes, sir.
Okay. So conclusion is 5-membered or 6-membered rings, chelate member ring are stable, and among them who is stable, it depends upon their hybridization, bonding, means conjugation. Such examples are. For 5-membered, I had given example of ethylenediamine, and for 6-membered, I had given example of acetyl acetonato ligand, AC minus. Okay, now the next factor is steric effect or steric factor, and in organic
The
chemistry,
recordings are
yes, it is on. What happened? Google recording now is not there. That access is there only for the few. Therefore, I have started recording. OBS recording is going on. Is it clear? Here, see, recording is going on.
okay, sir.
So steric hindrance, steric factor in organic chemistry, what you are studying, same concept is there in other kinds of molecules or the bonding. What that steric factor? Steric means related to the arrangement, spatial arrangement in space. If it is a crowding, and if the crowding, then the bonds also will experience some kind of the restriction. They also doesn't remain what the more stable. Strain remain on the bond. Why for? Because of steric hindrance. And that steric hindrance, if it remains less, then comfort will be there. Example, in bus if you are traveling and in a seat 2 passengers can sit, so 2 can sit comfortable. But suppose if third one comes, then uncomfort little bit will be there. Chances are there for while sitting in the classroom, sometimes on the one bench where 2 students should sit, you 3 students also do arrange, and a different way by doing circus you can arrange 4 students also. It depends, but somewhat comfort will not be there, and that uncomfort is considered in the steric hindrance or the steric effect. And the steric effect for this coordination compound says if that steric hindrance remains in the bonding, and because of that hindrance, that complex will be less stable. Less hindrance will result less stability. It's a general rough conclusion. Are you understanding what I'm saying?
Yes, sir.
So to make this concept clear, let me give example. Say ethylenediamine as an example. Ethylenediamine, how I represent, is just rough diet formula. NH2, CH, CH and NH2. Sorry, CH2, CH2 and NH2 is ethylenediamine. But in case if I substitute this terminal hydrogens by methyl, terminal hydrogens by methyl. Then that methyl derivative of ethylenediamine can be represented as, in spite of hydrogen, CH3. Number will be same, 2 nitrogen. Other were the same. End atoms, hydrogens are replaced. It is a tetramethyl derivative of ethylenediamine. Compared to hydrogen, certainly methyl molecule will be larger. Hydrogen is smaller, methyl molecule will be larger. CH3 will be larger. So larger molecule will take more space. More space. And what is happening? These nitrogens are donor. Lone pair is coming from this nitrogen. Lone pair is coming from this nitrogen. And they are donors. And because of that donation of lone pair, complex forms. But while donating, that lone pair also is one of the orbital. So that orbital, maybe that sp3 hybrid orbital present on the nitrogen, this orbital experience more repulsion in this case because methyl groups are there. Means nitrogen, one of the hybrid orbital where lone pair is there, if you consider one bond with the carbon, one bond with the hydrogen, one bond with the hydrogen. This is a case where in simple ethylenediamine. But if I replace this hydrogen by methyl group, see CH3 is a large group. Here also I replace by large group, say CH3. So among them coral will be there. They are fat. They will not be comfortable remaining near to each other. Though the separation among them is 109 degree 28 minutes, but they are not happy with that. So because of their coral, effect will happen here. So this which the bonds are there, the bond will experience strain. Strain will be there on the bond. And because of that strain, stress will be there. Or bond will not be stable. Bonding will not be stable. Molecule will not be stable. So steric hindrance here in methyl derivative will result less stable complex. Is this point clear?
Yes, sir.
Yes, sir. Yes, sir.
Yes. Now I want to go to the, if you go to the book, you will find the further different examples, but only I wanted to highlight because of steric hindrance, because of steric factor, because of steric effect, stability of complex will decrease, will be less. The next point is forced configuration. It is true the bond is between metal and ligand. Between them the bonding is there. Till now our approach was considering metal, our approach considering ligand. Now I have to consider both. In such cases what happens? Sometimes what happens, metal want square planar arrangement, but ligand does not want, because ligand also have their own orientation. Strain comes. Sometimes ligand wants square planar arrangement, square planar arrangement, but metal says not planarity possible. I give you example. If you consider porphyrin rings. Porphyrin rings are planar. These are ligands. I hope you understand. Giant chlorophyll kind of structure, large porphyrin rings are there and they are planar. So around metal, whichever the arrangement is there, skeleton is there, that whatever this is there, it is the planar. It is a planar. But suppose if this which the central metal is there and that metal has undergone hybridization and that hybridization is sp3. Will you answer this sp3 is a planar or non-planar? sp3 means tetrahedral arrangement. Planar or non-planar?
Planar.
Right, planar. Am I right? See, sp3 tetrahedral, simple way. Square you can understand plane. Plane means in one line, one go, you will reach from one point to other. Moving in one plane of symmetry. Here tetrahedral arrangement is there. Is it planar? Tripod stand likewise. These here three bonds are there and one bond is upside. Crucible or something you are keeping there on tripod stand. Is tripod is a plane?
No, sir.
No, it is non-planar. So metal wants non-planar arrangement and ligand wants planar arrangement. Here there is a forcing. Somebody force other. There are examples where ligand forces metal ion to align what want of ligand. Which is the example that I am considering now is with the porphyrin rings. And in porphyrin rings, demand of ligand is planarity. So if metal remains, example say beryllium, beryllium plus 2, that metal wants tetrahedral arrangement. So what is there? There is a dispute. There is a problem. So whoever will dominate will. So if metal dominates, then metal will settle ligand. You do changes. You do align. Stress will be there. You experience that. But if ligand is strong, ligand is giant, ligand is powerful, it will compel metal to be square planar. Its want is tetrahedral, but it will align in what? Square planar. It is a forcing. Student wants to play cricket. It is a want, but not allowed. Force is there. The psychological aspect. but physically also strain, if such things what you are doing comfortably, means we are comfort with that simple sitting on the ground or on the mat, that's sukhasana you can say. But if you ask to do padmasan, means where the legs are to twist, which is not our general habit, strain will be there, we are forced to do that, stability will be less. So in such uncomfortable situation, if you remain stable, mentally you will be strong, forget those things, and physically also the moments are there, and because of that the health improves. It was the logic behind it. My point of interest is a forced arrangement. If we force to align in that way, then there will be strain. So forced configuration compounds will be strainous, will be less stable. When will be their forced configuration? If ligand and metal are with different mentality. Ligand wants planarity and metal does not want forcing. Metal wants planarity, ligand does not want force. So one can force what the other. Examples in your book given are regarding what the force on metal. Ligand wants planarity and metal is forced to be planar. So in such a forcing, some repulsion or stress occurs, and the strainous or stresses situation is less stable. But if metal ion remains like copper plus 2, where DsP2 hybridization, square plane hybridization is possible, porphyrin will be happily bound with the copper plus 2. Comfort bind. So complex will be more stable. So where there is a forcing, that will be what the less stable. Student does not want to study, but we compelled to study, stability will be less. Want is there to study and instructions are given, some more encouragement will be there, stability will be what more. So our the last point of this chapter is forced configuration. If configuration is forced, then it is less stable. It is a conclusion. Example I had given, beryllium plus 2. Let me clarify that example. Beryllium, what's the atomic number of beryllium?
4.
4. So its electronic configuration 1s2, 2s2, 2p2. So this 1s electron, inner electron, if I do not count, then this 2s only one. In case of p, 3 orbitals are there. Maybe electrons are only 2. Let they be here 2 electrons. So beryllium can undergo. I am talking about here beryllium, but actually what? Beryllium plus 2. In case of beryllium plus 2, 2 electrons will be lost. So if you consider the loss of the electron at this point, time being, these 2 electrons are lost. Then some rearrangement also may possible. This electron also can go in what the other. So various possibilities. Anyhow, it is possible if it is forming the 4 bonds. If beryllium plus 2, I was wrong. Where is mistake? Do you know? I had committed a great mistake. Where is the mistake? Yes, where is the mistake? See, only 4 electrons are there. No, I represent 6 electrons. I wrote the configuration of carbon. So what should be there?
Yes, sir.
Yeah, these 2p2 electrons are not there. Not there. So in barium plus 2, these 2 electrons from 2s will not be there. So complete empty room. House is there, nobody is there. Means I like Mumbaikar build a house here and nobody remains in the house. Example I am giving. So building is there. 4 guests can come. They can enter. 4 guests. Which are those? Those ligands, lone pairs. Here one lone pair, second lone pair, third lone pair, and fourth lone pair. It is possible. And type of hybridization is sp3. sp3. 4 guests are there. Then beryllium can have only and only sp3. Other possibility is dsp2. But dsp2 orbital, d orbital is not there at all in the beryllium. So it can't undergo dsp2 hybridization, only way is sp3. So beryllium says I can't align in what the square plane element. But if ligand remains like porphyrin in chlorophyll structure, it's a giant molecule, so I'm not representing large molecule. Porphyrin planar, then porphyrin will force beryllium plus 2 to be in square planar arrangement or somewhat nearby. So beryllium does not want to be in planar arrangement, but because of that force, it has to align. So in such a forced configuration structure, stability is less. Therefore, for forced configuration, I had given you example of beryllium plus 2. In your book, in wording, whatever they have given is properly correct. But in diagram, they have given example of copper plus 2. Now, in case of copper plus 2, here by only simple VBT, we cannot give what the explanation. But this copper plus 2, undergoes the DsP2 hybridization. That one unpaired electron is there that we cannot accept. It's a limitation of the valence bond theory. But that copper plus 2 can undergo that DsP2 hybridization. And if it is undergoing DsP2 hybridization, then it can, there's a no need of force. It's a willingness will be there. So such complex is more stable. So whether there's a force during the bonding or not, that we have to understand, that we have to grasp, that we have to think. Then we can discuss about the stability is the point for the force conversion. So student, firstly, if I have to revise, I discuss first factor, that's the nature of central metal ion. In that we discuss charge density. In that we discuss, yes, second point for discussion under nature of metal ion.
CAP.
In that we discuss third point, complete
Classification of
class or category of
metals.
the metal. Under the second point, that's the nature of ligand, nature of coordinating group. Also, we discuss 3 points. What are the first point?
Base strength.
Best strain. Second point,
Covalent bonding.
right.
Covalent bonding.
Third point,
Concentration.
concentration of ligand. And today we completed the third aspect, that's the nature of coordinating group, especially in case of the chelation, nature of chelation. And why chelates are stable, that all things we discuss. In that, number of members, number of rings and number of members. These points I discuss. Then steric factor I discuss, and force configuration I discuss. With this, this portion of unit number 2 completes. What is this portion? Thermodynamic stability. It is related to bond formation and deformation. From next lecture, we should see a kinetic stability. Actually, it is the speed of the reactions, rate of the reaction. Means it is related to lability or inertness. At the beginning, I had given that explanation. So that point we will discuss next time. If you have any doubt, any question, feel free to ask. Yes, is there any doubt?
No, sir.
No, sir. No, sir.
Shall we stop now?
Yes, sir.
Okay, students, I declare here today's session or lecture is over.